Hello everyone. Welcome to Indian Nanoelectronics User Program here at CNNP-IIT Madras. This is Somnath Biswas from INUP-IIT Madras team Electrical Engineering Department, welcoming you all to this talk on oxidation process in semiconductor manufacturing technology. So this is the outline of the talk. So just to give a context, this talk will be mostly on the processes which are involved in depositing and growing silicon oxide. So you can see from the introduction, so we'll first discuss about the process definition and the classification of the oxidation process. It will followed by why silicon oxide. Why silicon oxide is so much important in semiconductor manufacturing technology. The second part of the talk will be process of growing silicon oxide, and the process is known as thermal oxidation. It is one of the most important unit processing step that is used in semiconductor manufacturing technology. So this will include the thermal oxidation process definition and classification of the process, followed by kinetics of thermal oxidation, controlling parameters of thermal oxidation process, and then exactly how we do the thermal oxidation process in our lab. The third part is the process of depositing silicon oxide. So mostly we'll be discussing about chemically vapor deposited oxide in this talk, even though there are many physically vapor deposited oxide techniques available. But in this talk, we'll be uh, mostly concerning on the chemical vapor deposited oxides. One of the process is the low temperature oxide deposition using LPCVD. We'll be explaining the kinetics of chemical vapor deposition technique and the controlling parameters of CVD techniques and why low pressure CVD is used. Followed by the later part of the presentation, I'll follow a brief discussion on another CVD oxide process, which is ICP-CVD oxide, and then follow up with the references that I've used in making the presentation. So now this is the introduction. So the first part is the process definition. So oxidation, as the name suggests, is a process of loss of electrons or increase in the oxidation state of a molecule, atom, ion, or element. So in silicon IC fabrication, the element of interest is silicon. Now the product of interest, like now, once we do the process, what we expect to get, it can be stoichiometric or non-stoichiometric silicon oxide. So the types of oxidation, like as far as processing technology is concerned, oxidation process can be broadly categorized into two parts. One is deposited oxide and other is grown oxide. So how we can actually grow oxides? This grown oxides, so there are three processing steps through which we can grow oxide, silicon oxide. So the first process is chemical oxidation. So here we take our silicon wafer and then we boil the silicon wafer in boiling nitric acid. So the nitric acid acts as an oxidizing agent and forms a silicon oxide. Now, the second part is anodic oxidation. So it is a two electrode system. So in two electrode system, we use silicon as one of the electrode and the anodic oxidation happens over there. The third most important part is thermal oxidation. And this process we are going to discuss majorly in this presentation. And this thermal oxidation process is again divided into dry oxidation and wet oxidation. Now, as far as deposited oxide is concerned, we can deposit oxide via the chemical vapor deposition techniques as well as physical vapor deposition techniques like sputtering. In this talk, in the later part of the talk, we'll be mostly discussing on two CVD techniques. One is low pressure CVD technique and followed by ICP CVD technique. Now, just to give a context, what does deposited oxide and grown oxide means, or what is the basic difference between a deposited oxide and a grown oxide? In case of a grown oxide, silicon from the substrate is actually a precursor in the reaction. Now, when the oxidation process occurs, silicon from the silicon substrate is actually consumed. Now, in case of a deposited oxide, silicon from the silicon substrate is not the precursor here. We provide some separate precursor gas. For example, it can be silane. So this precursor gas oxidizes in presence of an oxidizing agent and forms silicon oxide. So there's a second slide, like why SiO2 is so important. So as far as processing technologies are concerned, so SiO2 are basically used for the following processes. First is masking process. So you can see from the diagram. So if you want to do diffusion, if you want to dope your silicon substrate with certain dopant entity, you need to block certain region of silicon atoms. So in that case, SiO2 acts as a very good masking layer. Also, in case of ion implantation, where we can use photoresist as a mask, but we need a very thin layer of screen oxide to actually prevent any kind of damage to the silicon substrate. Now, the second important process is passivation of surface. So, for example, if you fabricated a device and you know that if the device is exposed to ambient environment, the electrical property of the device might get degraded over a long period of time. As a result, it's very important for us to passivate the device using an insulator. And the insulator that is widely used is SiO2. Hence, you can see in this diagram, it is a CMOS technology diagram. You can see that the devices which are actually N-channel FET and P-channel FET is actually passivated using this passivation oxide. Now, second is the most important part, which is gate oxide for MOS devices. As we know, the field effect transistor is a MOS structure with a metal oxide semiconductor stack. So the oxide, mostly we use very high quality SiO2. So that is also SiO2 also serves a purpose for gate oxide in MOS devices. Now, second is isolation of device. So here you can see two different techniques of isolating device. So once you fabricate your device, suppose you have a multiple number of devices, you need to electrically isolate those devices. So the two most common techniques used in isolating devices is low cost and STI. So you can clearly see in the first low cost technique, this region is isolated, electrically isolated from this region using this thick SiO2 layer. So this SiO2 layer acts as an isolation between this part of the device to that part of the device. Similarly, in case of STI or shallow trench isolation, you can see this. So this is a silicon wafer. The trench is made, and the trench is, you can generally cover the trench with the insulating material. And SiO2 is one of the insulating material that is used. And that insulating material actually insulate this part of the device or electrically isolate this part of the device to this part, right? Uh, so another one of the most important part is SiO2 is also used as a sacrificial layer in MEMS. So we know that MEMS has moving structures or release structures. So for example, you can see a polysilicon beam, which is a release structure, which is actually a hanging structure. So before the release, you can see this blue part is actually an SiO2 layer. So we deposit SiO2 layer, and over that we deposit the structural polysilicon layer. We etch this sacrificial layer and release our and suspend our polysilicon beam. So this SiO2 also serves its purpose as a sacrificial layer in MEMS device. Now the last part is pad oxides to reduce stress. So for example, in low-cost technique or in STI technique, we use silicon nitride as a mask for selective oxidation. So now if you directly deposit silicon nitride on silicon substrate, it increases the stress on the silicon substrate. So to reduce the stress, we generally have a very thin layer of pad oxide, and over that pad oxide, we deposit silicon nitride. And that pad oxide actually helps in reducing the stress in the silicon substrate. Now, as far as material is concerned, material properties are concerned, these are some of the properties that are listed. So as I've said, it can be easily selectively etched using a photolithography technique. So it serves as a mask for most common impurities. It is a very excellent insulator with high resistivity values. It has a very high breakdown strength, breakdown field. It actually has a very excellent. It actually serves as a very excellent junction passivation. So and also it has a very good stable bulk electrical properties. And lastly, silicon has a tendency of forming silicon oxide. So it actually forms a very stable and reproducible interface with silicon. Now, if we want to talk about what are the typical thickness of silicon oxide that we are talking about for different applications, we can see this. So this y-axis is actually the oxide thickness, and this is thermally grown oxide. So you can see the field oxides that we use to passivate device are in the size of maybe 1 micron or maybe 1.5 micron. So masking oxides that we use can be in the range of hundreds of nanometer, maybe 400 or 500 nanometer. So the pad oxides that we use to reduce stress are in the order of less than 100 nanometer. And the most important oxide, which is gate oxide that we use in field effect transistors, are actually lesser than 10 nanometers. And as we know, silicon has a natural tendency of oxidizing. So the native oxide that forms over the silicon surface is of the range of 1 nanometer. Now, as far as deposited oxides are concerned, again, it serves as masking oxides. And the thickness of the masking oxides are in the range of hundreds of nanometer. Now, once you fabricate a device, you know that you have multiple layers of metal uh, are there, and you need to electrically insulate all those metal layers. To electrically isolate these metal layers, we actually use deposited insulators, and this deposited insulators, mostly we use SiO2 also. So now let us go into the unit process through which we can thermally grow uh, silicon oxide. So the process is known as thermal oxidation. So thermal oxidation is a process of thermally growing a thin layer of silicon oxide, silicon dioxide preferably, on the surface of silicon wafer at high temperatures, where the silicon atoms in the wafer itself act as a precursor for the reaction. So now, as we know, if we keep our silicon sample exposed to ambience, it has a natural tendency to form silicon oxide. Okay, but the thing is that it is very difficult to get a very thick native film on the silicon oxide. So in order to get a thicker native film of silicon oxide on silicon sample, we need to subject the silicon wafer at high temperatures. And as a result, this thermal oxidation process, temperature plays a very important role. So this thermal oxidation process is again divided into two, as I've mentioned in my first slide. One is wet oxidation, another is dry oxidation. So these names are self-explanatory. In wet oxidation, this oxygen gas is bubbled through water, and which is kept at a temperature just below the boiling point. So actually, silicon, which is the solid phase silicon in the silicon wafer, reacts with gaseous water molecules and forms SiO2, which is solid, which is grown on the silicon substrate, and hydrogen gas is released as a byproduct. Now, this in case of dry oxygen, there is no presence or there is no involvement of water. Oxygen gas is passed into the furnace. Silicon, solid phase silicon in the crystal reacts with gaseous oxygen to form solid SiO2 over the silicon substrate. Now, the growth rate of wet oxidation is actually faster as compared to dry oxidation. The growth rate is much slower. Now, quality, if you look at the quality of wet oxide is actually not as good as that of dry oxide. It has lower density, lower dielectric strength. On the other hand, dry oxidation, it has higher density and higher breakdown voltage and dielectric strength as well. So the leakage current, again, if you have a wet oxide, the leakage current through the insulator is actually higher if it is a wet oxide. Now, if it is a dry oxide, the leakage current is much lower. So as far as application is concerned, wet oxides are used for masking, device isolation, and surface passivation. Dry oxidation generally has only one purpose, and that is we need very ultra pure thin dry oxide, and that actually is used as gate oxides in field effect transistors. So let us go into the kinetics of thermal oxidation. So we should know how this thermal oxidation process actually occurs. So it is a three-step process. So first process is transfer of the gas molecules to the outer surface of SiO2. So suppose this is your silicon wafer. You have a very thin layer of SiO2 that is grown over it, and you have the oxidizing species, which could be oxygen or water. So first thing is that these gas molecules should pass through the furnace and get transferred into the outer surface of SiO2. Now, once it reaches to the surface, it has to diffuse through the already grown oxide. So you can see that maybe if you have a thin layer of oxide over there, this oxidizing species has to diffuse through this oxide layer in order to reach this silicon present in the silicon wafer, right? So once the diffusion of gas molecules through the oxide is done, next the oxidizing species actually reacts with the silicon present in the silicon wafer. It breaks the silicon-silicon bond and forms silicon dioxide. So as you can see, there are three steps, major steps that are involved in the thermal oxidation process. Now, if you look at this figure, you can see, so if this dotted line is the original silicon surface. Now, as we keep the surface exposed to the oxidizing species at elevated temperature, we can see that silicon-silicon dioxide interface penetrates deeper into the silicon substrate, right? So now, for example, if we want to deposit X naught thickness of oxide layer, if we want to grow X naught thickness of oxide layer on silicon, you can see that it consumes about 0.44 X naught of silicon from the silicon wafer. So this is mainly because of the difference in the molar volume of silicon and silicon oxide. So silicon, if you look at, the molar volume of silicon and silicon oxide, the molar volume of silicon oxide is almost double of that of molar volume of silicon. As a result, if we do this measurement and if we check the thickness ratio of silicon and silicon oxide, it comes to be 0.44. So which basically means that if you want to grow X naught thick thermal oxide, 0.44 X naught from the 0.44 X naught of silicon from the silicon substrate will be consumed. So it is a very important thing that you need to remember. So now, as I've said, so the dry oxidation actually gives a better quality of oxide. So what do we do? Suppose if you need a thicker oxide, dry oxidation rate is very slow, so we can't do dry oxidation, right? So what do we have to do? We start with dry oxidation because if you do the dry oxidation, the silicon-silicon interface is better. Now then we follow it up with wet oxidation. So this wet oxidation will actually occur at a very faster rate. And then again, we finish the process with dry oxidation. The reason is because the reaction actually occurs at the interface. So if we finish the process after wet oxidation, the interface will be might get degraded. So we start with dry oxidation, then we go for wet oxidation for the thicker film, and then we finish with dry oxidation. So dry with dry is the basic protocol that most of the labs follow in order to get thicker thermal oxide of silicon. Now, if you look at the kinetics of thermal oxidation, if you look at this image, you can see, so there is, you can divide it into three parts. So this is a silicon wafer. This is the grown silicon dioxide, and this is the gaseous phase in the furnace of silicon. So now we can see there are three flux that is associated, F1, F2, and F3. Now this entire kinetics of thermal oxidation is actually developed by Deal-Grove, and we say it as Deal-Grove mechanism, and they have developed a model which actually encompasses all the three steps that are necessary for thermal oxidation. So you can see this. So if you see here, F1 is actually the transport of the oxidizing species in the gaseous phase from the furnace to the surface of SiO2. Now F2 is basically the flux of the oxidizing species through the already grown oxide layer. And F3 is the flux, or X3 basically is the rate of reaction at which the oxidizing species that has already reached silicon reacts with the fresh silicon over there. So if you look at F1, F1 is basically proportional to Hg, which is known as mass transfer coefficient. This is proportional to the diffusivity value of oxidizing species, diffusivity of the oxidizing species or the reactant in the gaseous phase. Now, Cg is the concentration of the oxidizing species in the gaseous phase. Cs is actually the reactant concentration at the surface in gaseous phase. Now, if you look at F2, F2 can also be written as d C0 minus Ci. C0 and Ci is the concentration gradient in the SiO2 layer that is deposited. So F2 is equal to d by Tox CO minus Ci. CO is the reactant concentration absorbed on the surface, and Ci is the reactant concentration that has already reached the silicon surface. And the third flux, F3, is basically surface reaction rate into the concentration of the reactant that has reached into the surface, right? So at steady state, this three flux has to be equal. F1 has to be equal to F2, has to be equal to F3. So now if you do some basic algebra, and here what we have done, we have replaced the concentration of the gaseous phase with the partial pressure of the gaseous phase using ideal gas equation, right? So, and if you do some basic algebra, and if you find the rate of growth is actually the rate at which the oxide thickness is changing with time. So which is dt ox by dt is equal to FSS by N, where N is the oxidation oxygen atom density in SiO2, right? So once we put this FSS value and integrate, we actually get a second order equation. So this is the second order equation where Tox is actually the thickness of the oxide that is grown. T is the time over which you have done the oxidation, and A and B are some parameters. So we need to dive deeper into this A and B. because these are very important parameters, right? So you can see how the A parameter and B parameter actually looks like, and also the tau parameter. So in the subsequent slides, we'll be explaining what these parameters actually means and how it controls the deposition, the growth rate of thermal oxide. So as you've seen in the last slide, the Deal-Grove model, it is a linear equation of second order. So if we approximate this equation for smaller t, we see that the thermal oxide thickness is linearly dependent on temperature, and the proportionality constant that is related to temperature is B by A. Hence, B by A is known as the linear rate constant. For longer time t, we can see that the thickness of the thermal oxide grown is has a square root dependence on time. The parameter that actually relates it with time is B, and it is known as the parabolic rate constant. Now, if you look at the graph, so we can see the oxide thickness with oxidation time. So initially, when the time is very less, we can see the growth rate is linear in nature, and as we increase in time, it saturates and it becomes parabolic, right? So there are some discrepancies of this Deal-Grove model. So one of the problem is that the Deal-Grove model actually are unable to estimate the initial oxide thickness growth. The reason is that the initial oxide thickness growth is dominated with some second order effects which are not considered in the Deal-Grove mechanism. So as a result, what you do, we extract the fitting parameter tau, and we consider that a certain initial oxide has already grown on the silicon wafer, which is TOX. And beyond that TOX, the Deal-Grove model actually catches the actual profile that we actually get after thermal oxidation. So TOX, the initial TOX, which is T naught, is basically of the order of 20 to 30 nanometer. We can see it from here, and if you extrapolate, we can actually extract this parameter tau, and we can put it in the Deal-Grove model equation. Beyond this oxide thickness of 30 nanometer, the Deal-Grove model given by the second order linear algebraic equation actually matches the experimental values properly. Now it is very important for us to understand physically how the growth rates are actually controlled. So as you have seen in the Deal-Grove mechanism, three fluxes are there: F1, F2, and F3. So the growth rate is actually dependent on the flux, which is the slowest among the three. So now it turns out that the flux F1, which is actually the rate at which the oxidizing species in the gaseous phase is being transferred from the bulk of the reactor to the SiO2 surface, the oxidation, the diffusion time is actually very fast. So as a result, we can ignore the F1 flux. So mostly the growth rate of thermal oxide is controlled by flux F2 and F3. So now for smaller time t, when the oxide thickness is very small, right? In that situation, the oxidizing species has to actually, so the oxidizing species does not has to travel more distance through the oxide layer. As a result, the growth rate is determined by how quickly the oxidizing species reacts with the silicon surface and breaks the silicon-silicon bond and forms SiO2. So for smaller t, the reaction is the growth rate is actually reaction rate limited. Now for longer t, as we've kept the sample exposed for a longer period of time, we have got a thicker SiO2 already grown. Now the oxidizing species has to diffuse through the already grown oxide layer in order to reach the silicon interface. In such case, it is found out that F2, which is the flux of the oxidizing species in the oxide layer, determines the growth rate, and that growth rate regime is known as diffusion rate limited. So now, as I've said, there are some limitations of the model. The limitations are the model is designed in such a way that it captures 1D model for planar substrate. So for heavily doped silicon, this model does not give accurate data. And as I've explained in the graph, for inner oxide, which is less than 20 to 25 nanometer, the model actually fails to capture the physics. Now, what are the controlling parameters of this thermal oxidation process? So there are 4 controlling parameters. One is temperature, second is pressure, third is crystal orientation, and fourth is substrate. Now we can see that if you come to this temperature, we can see that this parabolic rate constant and this linear rate constant and this parabolic rate constant has a dependency on surface reaction rate and also on the diffusivity. So for example, we can see that this linear rate constant, the temperature behavior is actually determined by Ks, as I have said earlier. So this linear rate, in case of the linear rate behavior, the entire growth rate is actually determined by the surface reaction. Now, in case of the parabolic rate, in case of the parabolic rate, the temperature behavior is determined by the diffusion constant, which basically states that the growth rate in the parabolic regime is actually diffusion controlled. Now, if you look at some temperature dependencies of the growth rate, we can see, for example, this is the parabolic rate B. So this parabolic rate B has a certain dependence on temperature. This is the Arrhenius plot. And so this is for dry oxidation, this is for wet oxidation. Now we can see the activation energy here is 1.24 electron volt. And in case of the activation energy in dry oxidation is 1.24 electron volt. And the activation energy for wet oxidation is about 0.71 electron volt. Now, as I've explained earlier, the parabolic rate constant is basically mass transfer limited or diffusion limited. So the entire growth rate is actually determined by how fast the diffusing species, which is, for example, oxygen in dry oxidation and water in wet oxidation, how fast this oxidizing species actually diffuses through the already gone oxide layer. Hence, we can see that in case of the diffusivity of oxygen through SiO2 is different than the diffusivity of H2 molecules in SiO2, we can see that there is a difference in slope values. Now, in case of linear rate constant B by A, as I have explained earlier, it is fully dependent on reaction rate. We can see that the activation energy for dry oxidation for linear rate constant is 2 electron volt. And in case of wet oxidation also, it is around 2 electron volt. This 2 electron volt is actually the energy that is required to break silicon-silicon bond, which actually suggests that the entire growth rate is controlled by the reaction. And by reaction, it means that how fast the oxidizing species is able to break silicon-silicon bond and form SiO2. Now, the second parameter which is important is pressure. So for wet oxidation, as you can see from the B by A and V values, both linear and parabolic rate constants are linearly related to partial pressure. So if you increase the pressure of the oxidizing species, the linear rate as well as the parabolic rate constant increases linearly. Now, in case of dry oxidation, we can see that there is an exponential kind of variation with pressure, and the N value is actually varied from 0.5 to 0.1. Now, one of the main reason can be since in dry oxidation, the oxidizing species is oxygen. So for oxygen atom, the dry oxidation rate is different as compared to oxygen molecule. Hence, there is a variation of N value from 0.5 to 0.1, depending upon whether oxygen atom or oxygen molecule is diffusing through the silicon oxide layer. The third part is parameters. Third parameter which controls the growth is crystal orientation. Now, clearly, the number of silicon atoms per unit area on a wafer surface depends on the crystal orientation, right? But what matters is the number of silicon-silicon bonds per unit area. Now, clearly, when you are operating, when the thermal oxidation growth is in reaction rate regime, it is so the reaction rate regime is controlled by how fast you break silicon-silicon bond. Hence, we can say that B by A, which is actually reaction rate limited, has a dependence on crystal orientation. On the other hand, the parabolic rate constant B, where diffusion rate limited regime is there, is independent of Ks and thus independent of the crystal orientation. Now, again, substrate doping also plays a very important role. For higher doping levels, there is an increase in B by A, hence it increases the deposition rate, the growth rate as well. This is probably due to an increase in crystal defect. If you have more substrate doping, that allows for faster volume expansion. there. So now we look at the thermal oxidation process that we do in our lab. So first is cleaning of the silicon wafers, RCA cleaning, which is very important step. So next, nitrogen gas and oxygen gas are the two most important gases that are used in this process. So as far as the furnace is concerned, we first keep the furnace idle with purging nitrogen flow. Then we keep the furnace idle with the process nitrogen flow. After that, we put the wafers, which are clean wafers, in the boat and load the wafers into the furnace. So now once the wafers are loaded, we ramp up the furnace to the process temperature in nitrogen ambience. So the reason is that, as we know that if we keep our silicon wafer exposed to ambient oxygen, it might get a native oxide form on it, and the native oxide that actually forms on the silicon surface is actually very bad quality of oxide. So we have to avoid this formation of native oxide formation. Hence, we need to keep the sample in the presence of process nitrogen while ramping up the furnace to the process temperature. So the process temperature that we use for this dry with dry oxidation is 1000 degrees centigrade. So once we reach the process temperature, we do temperature stabilization in presence of the process nitrogen flow. Once the temperature is stabilized, we need to start the dry oxidation process. As I've said in the previous slides, the protocol that we follow for thicker oxide is first we go for dry oxidation, then wet oxidation, and then followed by dry oxidation. So once the temperature is stabilized, we turn on the oxygen valve for dry oxidation and stop the nitrogen valve flow. Second, for wet oxidation, we turn on the bubbler. So the oxygen gas actually flows through the bubbler and carries the water stream along with it. So we do the wet oxidation for a certain amount of time. Then we again finish it with dry oxidation by turning on the nitrogen valve and by turning on the oxygen valve and turning off the bubbler. After that, it is once the dry wet dry oxidation is finished, we anneal the substrate in nitrogen ambience. This is to actually reduce any defects that might have occurred during the process. So during this process, we turn off the oxygen valve and turn on the nitrogen. So once the annealing process is done, we ramp down the temperature in the presence of process nitrogen. We ramp it down to room temperature. Once it reaches room temperature in presence of process nitrogen, we pull out the wafers. Similarly, again, we keep the furnace idle with process nitrogen flow, and then again idle with purge nitrogen flow and repeat the process. So if you look here, the furnace, it is something, so it's a quartz furnace, and you can see that you have controls over the oxygen gas and nitrogen gas through valves. So, and you can, for dry oxidation, you don't have the bubbler connected. In case of wet oxidation, you turn on the bubbler so that the oxygen molecule can actually flow through the bubbler and carry the steam along with it. In case of dry oxidation, we don't have any bubbler connected to it. And inside the furnace, we can see in a quartz board, the samples are actually loaded vertically stacked so that we can do batch processing. If you look at the oxidation process timing diagram, we can see temperature versus time. First, during loading, it is at room temperature. We keep on the nitrogen gas valve on. We ramp it up in presence of nitrogen. We perform the oxidation process. While performing the oxidation process, we turn off the nitrogen valve and turn on the oxygen valve. Once the oxidation process is finished, we turn off the oxygen valve and turn on the nitrogen valve at process temperature, and we do annealing. Once the annealing is done, we ramp down the temperature to room temperature. While ramping down again, the nitrogen gas valve is turned on and the oxygen gas valve is turned off. We ramp it down to room temperature, unload the sample, and use it for subsequent processing. So here you can see some of the thermal oxidation process that we have carried out in our lab. So this is the sample. This is the silicon sample after RCA cleaning and before the oxidation step. So you can see two samples are there. So the first sample, we can see we have done dry oxidation for 15 minutes, followed by wet oxidation of 15 minutes, and then dry oxidation of 15 minutes, and annealing of 20 minutes. So once we've done the process, we've measured the data using ellipsometer, and from the ellipsometry data, you can see the surface plot of the oxide thickness that have grown on the silicon surface. The average thickness was found to be 139 nanometer. The roughness was about plus minus 10 nanometer here. In the second sample, we have done it for a bit longer time, dry oxidation again for 15 minutes, followed by wet oxidation for 1 hour 45 minutes, dry oxidation of 15 minutes, and then annealing uh, at process temperature for 20 minutes. The average thickness, it was found to be much thicker because we have done the wet oxidation for more time period. And the average thickness was found to be 581 nanometer. And the roughness was again in the range of plus minus 10 to the 10, 15 nanometers. Again, we can see from the color that you can see from the color chart. So this the first sample, which was done for about 15 minutes wet oxidation. This bluish color chart actually corresponds to a thickness of about 120 to 140 nanometer. And accordingly, we also got average thickness of about 139 nanometer from the ellipsometry data. In the sample two, we have done it for much more period of wet oxidation, and hence we achieved a thicker film. And you can see a greenish color of thermal oxide that is grown on the silicon wafer. If you look at color chart for green color, the range of thermal oxide is in the range of 500 to around 600 nanometer, and we have also achieved around that thickness from our ellipsometry data as well. So this is the image of the thermal oxidation furnace here at CNNP IIT Madras, and you can see how the process are done here. So as you've seen, so in the last few slides, I've discussed how thermal oxidation process is done, what are the parameters that control thermal oxidation, how we do the process in our lab, and how the samples looks like once we do the thermal oxidation process. The second part of the lecture is the later part, is very brief discussion of the other technique, which is the deposition of silicon oxide, and the process that we here will be considering is a chemical vapor deposition process, precisely low pressure chemical vapor deposition process, which we will be covering in the subsequent slides. So now, what is a chemical vapor deposition system? So here, chemical gases or vapors react on the surface of solid, producing solid byproduct on the surface in the form of a thin film, right? So what happens? So as you have seen, this is a process through which we can deposit oxides. So clearly, here the silicon substrate doesn't act as a precursor. We actually flow some precursor gas, which is silane here, right? So here we have a gas delivery system. So through this gas delivery system, we transport the reactants. This reactants actually diffuse through the boundary layer. This in gaseous phase, it diffuses and adsorbs on the surface of silicon. On the surface of silicon, it actually a surface reaction occurs and nucleates in the form of islands. These islands merge to form continuous films. So once the chemical reaction occurs, byproducts are formed. These byproducts are deabsorbed from the substrate that diffuses through the boundary layer, and the diffusion of the byproducts through the boundary layer, and then through the exhaust, we can actually take out the byproduct. So ideally, there are three ways by which the CVD process are done. One is atmospheric pressure CVD. The second is low pressure CVD, and third is plasma enhanced CVD. So let us look into the kinetics of chemical vapor deposition, which is given by a Grove model for thin film growth rate. So as we remember that in case of thermal oxidation, three fluxes were there which control the growth rate of thermal oxide. Here, the case is different. Here we have just two fluxes. One flux is F1, which is basically the transport of the oxidizing species in the gaseous phase from the bulk of the reactor to the surface of silicon. And second is the flux, which determines the rate at which the oxidizing species that has already reached the silicon surface reacts with silicon, right? So F1 is again equal to Hg into Cg minus Cs. Hg, as you've seen in the earlier slides for thermal oxidation, is mass transfer coefficient, and Cg is the concentration of the gaseous reactant in the bulk of the reactor, and Cs is the concentration at the surface of silicon. And the second is flux F2, which is Ks, which is surface reaction rate, into Cs. Cs is the concentration of the gaseous of the oxidizing entity at the surface of silicon. Now again, under steady state condition, F1 should be equal to F2. And if you do some basic algebra, we can see that the rate of growth, which is the rate at which this oxide thickness varies with time, is proportional to the partial pressure of the gaseous phase of the oxidizing agent. It also depends on a factor called Kt. So now what is KT? KT is basically proportional to mass transfer coefficient and surface reaction rate, which is Hg and Ks, right? So now if you look at KT, so for Ks much higher than Hg, we can actually approximate this growth rate to be a function of only mass transfer coefficient. So as I've said earlier, if among F1 and F2, the growth rate is basically determine the step which is slow. In case of if Ks is greater than Hg, which basically states that the mass transfer coefficient is much smaller than the surface reaction rate, uh, it basically states that the reaction is diffusion rate limited, because the flux F1 is the flux that is controlling the the deposition rate of the thin film. Now, in case of if Ks is lesser than Hg, then it turns out that flux F2 is slower as compared to flux F1, and hence we can say that the deposition is mostly controlled by the reaction at the surface. So now let's look into the parameters that control this CVD process. So the most important parameter is temperature. So the activation energy for a surface reaction is much higher than the activation energy for gas diffusion. So as we have explained in the last slide, the two regimes of operation that actually dominates in this CVD process is one is diffusion limited regime and other is surface reaction limited regime. So we can see that this mass transfer coefficient Hg has a polynomial dependence on temperature. On the other hand, the surface reaction rate has actually exponential dependence on temperature, which basically states that the activation energy for surface reaction is actually much higher than the activation energy for gas diffusion. So at higher temperature, we can actually now we can say that at higher temperature, Ks is much greater than Hg because of the exponential dependence of Ks with temperature. So as we have explained in the last slide, that if Ks is greater than Hg, then the thin film deposition is basically controlled by the diffusion control regime or by the flux, which is F1. So in the diffusion control regime, the deposition rate is actually very sensitive to the variation in the gas flow. So the chamber design is very important in such case. Chamber must be designed in such a way that best possible flow uniformity and control is achieved. Uniformity and control is achieved so that we can have a uniform deposition of thin film. Now, at low temperature, as you have seen, at low temperatures, the deposition will be reaction control regime. Ks will be much smaller than the mass transfer coefficient. In this regime, the diffusion rate is actually very sensitive to the variations in temperature. And the chamber, if you are operating if you are operating the chamber at low temperature in the reaction control regime, it is very important that we should achieve best possible temperature uniformity and control so that an uniform deposition rate is achieved over the entire substrate area. So now from the graph, we can say that this is the Arrhenius plot, logarithmic scale of the growth rate and the reciprocal of temperature. We can see for higher temperature, as we have seen, Ks is much greater than Hg. And the growth rate is actually dependent on Hg. And Hg has a mild polynomial dependence on temperature. So we can see that the growth rate is almost constant with temperature when the process is controlled by is controlled by diffusion. So now, but as we reduce the temperature, the mass transfer coefficient value increases, and as mass transfer coefficient value increases, what happens? The process actually enters into reaction control regime, and in reaction control regime, we can see that the growth rate has an exponential variation with temperature. Now, if we take both the effects into consideration, the net growth velocity or the net growth rate profile with temperature actually looks like something like this, right? So for higher temperature, which is controlled by mass transfer limit or diffusion control, the growth rate is almost independent of temperature. But at lower temperature, where the regime is controlled by surface reaction, there is a high dependence of the deposition rate with temperature. So now the second factor that is very important is pressure. Now we can see that as we reduce pressure, the mass transfer coefficient increases. So by decreasing the pressure from 760 torr to 1 torr, Hg is basically increased by 100 times. So you can see the Hg value at 760 torr was this. But as we reduce the pressure, the Hg value has increased. Now with reduced pressure, the net growth velocity is something like this. So now what it has happened is by reducing the pressure, what we have achieved, the reaction rate regime has extended to higher temperature with high deposition rate. Now we can see that in the second curve with lower pressure, the growth rate is for over a larger range of temperature, the growth rate is actually reaction rate controlled. And hence comes the utility of low pressure CVD in an atmospheric pressure CVD uh, where the pressure is high. With higher pressure, the mass transfer coefficient is also less, and hence the entire process is actually mass transfer control. And since it's mass transfer control, it is very important in atmospheric pressure CVD that the chambers are properly designed so that the mass transfer of the gaseous reactants can be done properly to get a uniform deposition. But in case of a low pressure CVD system, as we have seen, as we have increased the Hg value, the reaction rate regime has extended to higher temperature, and now the entire deposition process is actually governed by temperature. So we need to have a furnace where the temperature control is very high. Hence, in case of APCVD, cold wall reactors are used where temperature is not a very important parameter for deposition. But in case of LPCVD, since temperature uniformity is very important, a hot wall reactor with a very good control of temperature is required so that uniform deposition of thin can be achieved. So LPCVD, low pressure chemical vapor deposition. So it is a material synthesis method in which constituents of vapor phase at sufficiently lower pressure than the atmospheric pressure react to form solid film at some surface. So here, as I've said, the gas pressure is around 1 to 1000 millitorr. If you consider a atmospheric pressure CVD system, we do the thin film deposition at atmospheric pressure, which is about 760 torr. So here clearly we can see that in an LPCVD furnace or in LPCVD reactor, the gas pressure is about 3 times in order lesser than the pressure that we have in APCVD reactors. So generally we use LPCVD to deposit low temperature oxide, silicon nitride, polysilicon, etc. So the process temperature here is around 500 degrees centigrade, which is much lesser than the temperature that we use in thermal oxidation. Now, better step coverage and uniformity than atmospheric pressure CVD systems. Now, as you know, by reducing the pressure, uh, the deposition rate of thin film is actually reaction rate limited. So, since it is rate limited, there is a very less dependence of the thin film that is grown in LPCVD furnace on gas flow. So on the other hand, since the deposition rate is reaction rate limited, it is very sensitive to temperature. So any variation in temperature throughout the furnace can lead to a deviation in the deposition thickness of the thin film. So now, as I've said, LPCVD is a hot walled reactor. So the walls of the furnace also gets heated up, and as a result, since the deposition is dependent on the temperature, there are depositions on the hot walls of the reactor as well. As a result, it requires very periodic cleaning up of the furnace. So now, if you go into this LTO deposition, how the chemistry works. So as I've said, it is in my first slide, it is a deposition technique, and we use the silicon. The silicon in silicon dioxide actually comes from silane gas. So the silane gas is the precursor, which is in gaseous state, and reacts with oxygen in gaseous state, and then forms this thin film of SiO2 on the surface of the silicon substrate, and hydrogen gas is released as a byproduct. So now if you can see here the sample, so this is the LPCVD deposited sample done in our lab. On the other hand, on the right, you can see the ellipsometry data. The ellipsometry data shows the variation of the thickness of the LPCVD LT on the sample. The average thickness is found about to be 720. So you can see the LPCVD reactor that we use here at CNNP IIT Madras. So the standard recipe that we use here is we use a pressure of about 300 millitorr, So you can understand it is 3 order lesser than the atmospheric pressure. The temperature that we do is at 450, which is substantially lower temperature than thermal oxidation. We did for about 2 hours. Silane flow rate was about 17 and oxygen was 70, and we achieved an average thickness of 720 nanometer. Okay, so now let us go into inductively coupled plasma enhanced CVD. So before going to ICP CVD, so as you know that so the CVD system has basically three categories. One is the atmospheric pressure CVD, the LP CVD, as we explained in the last slide, and the third one is the plasma enhanced CVD. So what happens basically, for example, if you want to deposit at lower temperature, it is very difficult to initiate some chemical reaction at very lower temperature. Hence, the deposition rates are very lower. So what is the solution? So in a plasma enhanced CVD system, we add energy to the reactants by using an RF plasma. So by using that RF plasma, instead of providing thermal energy, we actually provide energy to the reactants by using an RF plasma. So, uh, so now what the inductively coupled plasma enhanced CVD does? So the ICP CVD uses an inductively coupled coil. The inductively coupled coil is connected to a RF source of 13.56 megahertz. So this RF current through the coil generates a magnetic flux. This RF magnetic flux induces an RF electric field. This induced electric field, this induced electric field accelerates the electrons, which creates a very high density plasma. Now, in case of a normal capacitively coupled RF plasma system, the control is actually very less. Now, if we consider like what are the parameters that determine the deposition in a plasma enhanced system, two important parameters are the ion bombardment energy and the gas pressure. So the problem is that the control is less in a normal capacitively coupled RF plasma system. But here, because of this inductively coupled coil, the ion energy control is independent from the plasma density. So hence the control is better, and because of the control of this ICP power, we can have a higher deposition rate and also a controlled deposition rate in ICP plasma enhanced CVD. So here you can see, so this is the ICPD system, ICP CVD system here in our CNP IT Madras lab. And some of the recipes that we follow in depositing SiO2, one we have a high deposition rate recipe where we use so we basically use silane and nitrous oxide as the precursor gas. Here you can see that we have a extra control knob, which is ICP power. Using this ICP power, we can control the deposition and we can see that in the high deposition rate, we can reach up to a deposition rate of 60 nanometer per minute. And in case of low deposition rate, we can actually you can actually have a deposition rate of about 10 nanometer per minute as well. So to conclude, so the entire talk was actually consisted of thermal oxidation process, then the CVD process, especially low pressure CVD process, and then finished up with the inductively coupled plasma enhanced CVD. So clearly, the dry oxide, as I've seen, the dry oxidation and wet oxidation actually occurs at a very high temperature, about 1000 degrees centigrade. So we provide thermal energy in order to for the oxidizing species to diffuse and react with silicon. In case of the LPCVD plasma system, we've seen that the process occurs at around 450 degrees centigrade. So basically, we provide this thermal energy, which initiates this silane and oxygen gas to chemically react and form thin films of SiO2 over the substrate. Now, in case of ICP PCVD process, we have seen that by using plasma, we can actually have a deposition at much lower temperature. We are talking about temperature of about 70 degrees centigrade. So almost some times more than the room temperature, uh, uh, we can actually do this ICP-CVD oxide deposition. So that is a very important factor. Like if you want, if temperature is a very important role that plays in your processing, then you can actually choose the particular process which is beneficial for the device fabrication. If higher temperature, if it is advised that if it is advised to avoid higher temperatures, then clearly we can go for lower temperatures, LTO, or maybe a much lower temperature ICP-CVD grown SiO2 as well. So these are some references. So these are 20, 30 years or 40 years old literatures. So there are standard books which has which actually has contained all this material of the talk. So it's very standard. Three books are available: J.D. Plummer and Deal and Griffin book, S.K. Gandhi or VLSI fabrication principles, SMZ on VLSI technology. This three books can be very useful if you want to dig deeper into the processes and how if you want to know more about the process, you can go and check these references. So hopefully this talk will help you to get a better insight of the processings, mostly the thermal oxidation and LPCVD process. So the next video will be hands-on video on thermal oxidation. Till then, thank you.